So thank you very much. And I want also to thank the organizers for inviting me to this meeting. So we're going to go back to experiments for a little while and back to NV centers also. So before that, here you see I want to talk about magnetic chirality. So let me first specify what I want to talk about. So chirality, if you look for the definition, it's the aspect of a structure or property that renders it distinguishable from its mirror image. So that's your answer. And this was introduced by Kelvin in 1904. And actually, experimentally, Pasteur found it in chemistry way before. And it's very important, in particular in chemistry and biology. In magnetism, what I will call magnetic chirality is a quantity that should indicate the sense of spin rotation when moving along an oriented loop or an oriented line. So if I look at a spiral, this one is going to rotate counterclockwise, this one clockwise. If I look at a skyrmion, again, you can have the two options. And why? Why is it interesting? Because looking at this, finding the chirality of a magnetic texture can give us insight about the magnetic interactions inside the material. Are the structures stabilized by dipolar effects or by other interactions? And in particular, the interaction that I would be interested in is the Jarushinsky-Moreya interaction. So for those who are maybe not so familiar with it, this is an antisymmetric exchange interaction that requires spatial inversion symmetry breaking. And basically, it wants to make the magnetic moments rotate. And depending on its sign, the rotation will be rather clockwise or rather anti-clockwise. And so if you have objects that are rather stabilized by dipolar coupling, you don't have a favorite rotational sense. And you can have, for example, like here, coexistence of clockwise and counterclockwise skyrmions, for example, in the same material. On the contrary, if your skyrmions, for example, are stabilized by this Jarushinsky-Moreya interaction, they all have the same rotational sense, necessarily. So this is already a very good way to know if DMI is important in a material, if all your objects have the same rotational sense. And how can we prove it? So you have two ways. You can first directly measure the direction of the magnetization and find out if it's rotating or not. So you can do that with various techniques. Here it's Lorentz transmission electron microscopy. Or you can go for NV sensing and measure the stray field which is produced by the texture. But then you have to very carefully analyze it quantitatively. So this was done, for example, here for domain walls some years ago, where you can see the black dots are the stray field profile above this wall experimentally. And here you find that your profile corresponds to a Bloch wall rather than a near right or near left domain wall. So with a stray field profile, you can find out the chirality and the internal structure, actually. So the technique I'm going to use today is scanning NV magnetometry, and you know everything about it already. So I won't spend much time on this one. Just one thing, I'm not going to talk about these complicated sensing protocols with microwave pulses and so on today. When I measure stray field, I just do this, optically detecting magnetic resonance, and there will be a little bit of measurement of the relaxation time afterwards, but I will explain it to you. And we also do that inside a scanning probe microscope. So again, you saw that this morning. We have a tip made of diamond. We have a single NV center at the end of the pillar. We have a confocal microscope above the tip to send the green laser and collect the photoluminescence. We have the sample below. And something which is very important, especially if you want to quantitatively analyze your data, is this distance here between the NV center and the surface. So that is going to give you the spatial resolution of your measurement, and also it's very important if you want to analyze your stray field profile. Just a quick picture. This is one of our setups. You have 2 towers of piezoelectric elements. On top of one of these, you have the tip at the green dot here, which is a laser. You have the sample on the other side, and the objective above. So before we go to DMI and chirality, I just want to show you what we can do with regular magnetometry. And in particular, we can look at antiferromagnets, something that not so many other techniques can do. And an example of a material that we looked a lot at is bismuth ferrite. So bismuth ferrite is a very fancy multiferric material. So you might have heard about it because it's almost the only one which is multiferric at room temperature. And it has a quite complicated magnetic texture. So at the order 0, it's a G-type antiferromagnet. But actually, this antiferromagnetic order is modulated. There's a cycloidal modulation of the order with a period of about 64 nanometers. But if you look at this and think that our NV will be 50 nanometers above, this is a completely compensated texture. So there should be no stray field at 50 nanometers from this. So we should not be able to see it. There is a third part of the magnetic order, which is small spin density wave, which is locked onto the cycloid. So basically, the moments are tilted away from the plane of the cycloid a little bit, which is creating then a weak moment that we are able to detect. And the nice thing is that this is always locked onto the cycloid. And this is coming from another type of this Strauschinsky-Moria interaction, actually. And so what we can do then is take our microscope, put a BFO sample in there, and have a look at the texture. So what you see here is actually this cycloidal modulation above the surface of a bulk crystal. And you see it's quite complicated. We didn't expect that. For bulk crystals, we expected a single direction of propagation of the cycloid. So we were a bit surprised. So then we confirmed this by doing resonant X-ray scattering, which is also a surface probing technique, but on a much larger scale. Here the beam is a few microns, and here this image is 1 micron, so much larger scale. And you see what you get. In a K-space, you get an ellipse, telling you that actually, yes, the wave vector of this cycloid modulation is rotating, and it's not a cycle, but an ellipse, because the plane of this K vector is not the surface plane, it's the 1, 1, 1 plane. So what this tells us is that there is a surface effect on the bulk crystals that is kind of destroying the anisotropy that we expected, and that in this case, the propagation vector of the cycloid is free to rotate inside this 1, 1, 1 plane. And also, since we have this kind of free rotation, we can have defects in there. So if you look closely at the image, you can find these 3 types of topological defects that you can find in any lamellar system. This U-turn, the pi disclination, or this Y-shaped defect, the minus p disclination of the H dislocation. And the nice thing is that we have them in an antiferromagnetic multiferric material. So it means we can, for example, try to control them with electric field at some point if we would like. So this was the first example of what we can do with scanning NV microscopy, looking at magnetic textures. But here, there is the trick. There is a spin density wave that helps us. What happens if we don't have it? If we have a really pure antiferromagnet, fully compensated? Then we will probe something else. We will not probe static magnetic field, we will probe magnetic noise. So what I call magnetic noise is randomly fluctuating magnetic field. And this was proposed actually by Benedetta a few years ago, that this noise will be, let's say, different if you are inside the domain wall or inside the domain in your antiferromagnet. And so it means that if we can probe it, we have a sample, there's thermal excitation in there. If we are in a domain, we will detect some noise. And if we are above the domain wall, we should detect something else. So this should help us localize magnetic texture in an antiferromagnet without the need to be able to detect the tiny stray field that could come from a real compensating antiferromagnetic texture. So before I show you how we did it, just let me explain quickly what the noise does to the NV center. It accelerates its spin relaxation. So if you are no laser, room temperature, you are in a thermal equilibrium state with the three states equally populated. You plug in your laser, you're polarized in the state 0. If you turn the laser off, the system is going to relax toward this thermal equilibrium state. And the way you can measure the relaxation time is basically by doing exactly that. So I show you there. You first have a pulse to polarized in the bright state. You turn it off, you wait some time, and you turn it on again to read the state. And you will get a decay, which you can see here in the blue curve. And for NV in a bulk diamond, you get a few milliseconds, usually at room temperature. And then what we did is we brought a wire, we sent noise inside that created magnetic noise. And when we turn on the noise, you see you get a crazy drop of this relaxation time. If your noise is overlapping, the noise if your spectral distribution of the noise is overlapping with the NV frequency. And so then, next question, what does this acceleration of the relaxation do on the emitted photoluminescence? So then you can just use a very simple model of the NV with 3 levels like this. And you will have a competition between the laser that is polarizing your NV in the bright state and your relaxation that wants to go back to the thermal equilibrium. And so we saw that this relaxation depends on the spectral field density of the noise. And so now, with this model, this is what you expect for the photoluminescence. If your relaxation time is very long, so slow relaxation, so low noise, you expect that your laser will efficiently polarize your system in a bright state. If you increase the relaxation, shorter relaxation time, your polarization will not be as efficient and you will see a drop in the photoluminescence. And so yeah, low noise, high noise. And using the setup I just showed on the previous slide, we could actually check it. And this kind of works, this simple model. So now, maybe you have a question before I continue? No? OK. So now let's do the measurement. So the sample we took is a synthetic antiferromagnet. So actually, we got samples from 2 different labs, the LAF in Palaiseau and SpinTech in Grenoble. And this sample is basically 2 layers of cobalt that are coupled antiferromagnetically. So it's a bit cheating. It's not a real antiferromagnet, but it's very convenient to do this experiment because then we know that if we are a little bit above the sample, we will detect a small stray field because this layer is closer to the NV than this one. So then we can do both and check that our noise imaging is working properly. So this is what you get. So this map here is just the photoluminescence of the NV center when we scan above the surface. So you see these dark lines, and if you measure the stray field, you will find that this is exactly what you expect for a domain wall in this type of double layer structure. So now the question is this contrast here really coming from noise? And to do that, we measure again this T1, so you know how to do it now. So we first did it with the tip far away from the sample, and we measured something in the millisecond range again. And then we brought the tip close to the surface, but above the domain, in a bright area. We see a first drop, and then we bring the tip above a dark line, so on the domain wall, and we see a second significant drop of T1. So there is noise coming from the sample, as this noise is stronger above the domain wall. How can we explain that? So this noise is obviously coming from spin waves inside the material that are thermally activated. And if you compute the dispersion of the spin waves in this sample, first on the domain here, you see you have a gap which is coming from the magnetic anisotropy. And in our case, the gap is just above the frequency of the NV center. So we are not really sensitive to the noise that is coming from spin waves inside the domain. We still, you see, we got an effect. We saw a first drop, but because this is actually super broad, because there's a large damping in this material, so we probe the tail. If you look at what happens inside the wall, the gap is closing because the internal field inside the wall is compensating the anisotropy. And now you have modes that are exactly at the frequency of the NV center. So you are much more sensitive to this noise. That explains the further decrease of T1 when you bring your chip above the domain wall. So this allows you to nicely localize textures. And you can actually compute the noise map that you expect, and you see a very good agreement with your experiment. Now, in this kind of material, you can also apply field, and then go back to 0 for the measurement, and you nucleate things. So here we have some big bubbles, and here we have a nice skyrmion, for example. And if you look at this skyrmion here, looks like, so, okay, resolution is not that good, but you don't see a full ring here. You kind of see only half of it. Now comes the question, is it just that this guy is deformed and we don't see it properly, or is it something that we should dig in? So we looked at many of them. So in this sample, we expect counterclockwise skyrmions. We know it because the Jarzynski-Murray interaction here comes from the platinum-cobalt interface, and this is very well known that this is creating counterclockwise textures. And so we looked at 20 of them roughly, and you see that your ring is never fully uniform, but it's not so clear from there that there is a pattern. So what I did is that I extracted the PL signal around the contour of the skyrmion. So usually there's always an ellipse that you can fit on there. And I plotted the variation of the PL as a function of this angle here. So you get the colored thin lines here, and if you take the mean value, you get this line that shows that there is indeed a sort of pattern coming out. And what we see is that around 0, we get a stronger noise. So what is breaking the symmetry here is this direction of the NV center quantization axis. So in our case, this is 60-degree out of plane and along the x direction. So it's like this. So this preferred direction here comes from the direction of the NV axis, actually. And you can compute, again, the noise map that you expect for a nicely round skyrmion. And you can also add a little bit of disorder to mimic the experiment. And you see here that you expect, so this is the noise level, and this is the PL. So remember, high noise, lower PL. So we see a peak here, which corresponds, as we expect, to dip in the experiment. So our data fits with Néel counterclockwise skyrmion, just from the noise. Yeah?
This might be a nice question, but you also see a dip at 180, but there's not a corresponding bump in the noise level?
Yeah.
Is there an explanation for that?
No. Well, this sample is very disordered. As you can see, the skyrmions, they all have different shape, so it might be just statistical noise from disorder. I can't really tell more about it. But then what you can do is compute the noise distribution along the contour that you expect for the other types of skyrmions. So skyrmions, you can have them clockwise or counterclockwise, and you can have them Bloch or Néel. So it gets four different types. And you see that the stronger noise at 0 is only there for Néel skyrmions. For Bloch, it's not there. So our data only fits with Néel skyrmions, which is what we expect from a platinum-cobalt interface anyway. And if you compute the stray field map that you expect in this type of synthetic antiferromagnets, you see that for Bloch or Néel, indeed, it's going to be very different. But the difference between Néel left and Néel right, if you have disorder, it's going to be quite difficult to make. This is roughly the same stray field level, roughly the same pattern. But one other thing that you see from the calculation is that the level of noise here is significantly stronger than here. And this we didn't expect. Another question is, first, it means that we could be able to distinguish clockwise and counterclockwise from the noise amplitude. And then, why? And then, does it also happen for domain walls? So, let's try to understand all that. So first question, do we also expect this from domain walls? And the answer is yes. So looking at counterclockwise or clockwise rotating texture, it's similar to looking at the sample from the top or from the bottom. You flip your sample, you rotate the other way And here is the noise map that you expect. So this is our counterclockwise rotating sample. We are usually probing it from above. We expect a strong noise. But if we look at it from the bottom, so as if we had clockwise rotating texture, we expect a much lower noise also for the domain walls. So now that we know we also expect that, we did the experiment. So this is, again, the initial sample. So our 2 cobalt layers on a tantalum substrate. And then we did our colleagues in Grenoble, they grew the sample on a membrane. So it's 20 nanometers thick, and we can probe the film from below. So this way we can actually do this map here. And what you see is that in the stray field map, I nicely see the domain walls, but in the noise map, we can hardly see them. There is a very faint signal, but I don't think you see it from there. Yeah, maybe a little. But basically, it's not there. So this is as expected from theory. So you might raise the question, but here you are 20 nanometers further away, indeed. But this experiment is done with a tip which was flying a little bit further away. So basically, there's less than 10 nanometers difference between these two images in height, and it's not enough to explain this complete disappearance of the signal. So why? So we need 2 ingredients. The first one, and I will quote our colleague Thibaut de Volder from the Citroën for that, a spin wave is like a fridge magnet. So what does it mean? You might be familiar with this arrangement of magnetic elements, which is called a Holbach array. In this case, basically what's happening is that the in-plane part of the magnetization pattern, it's compensating the effect of the out-of-plane part on one side, and it's adding up with it on the other side. So in the end, what you get is basically on top of your texture, you have a lot of field, and at the bottom, you have a very small field. And if you look at a spin wave, so processing magnetic moments in an in-plane magnetized texture, so in our case, the center of the domain wall is an in-plane magnetized texture, you can actually see the variation of the magnetization fits with this type of texture. So it means that the spin wave will create field only on one side. And depending on its k vector, it's going to be either up or either at the top or at the bottom of the film. So this is our first ingredient. Second ingredient is, again, Tarushinsky-Morier interaction. So this interaction creates a non-reciprocity in the dispersion of the spin waves. So basically, your dispersion is not symmetric. And so for this plus k and minus k, you expect a different frequency of your spin wave. And it means that with our NV, since we are filtering in frequency around this magnetic resonance frequency of the NV at 2.87 gigahertz, with the asymmetry from DMI, we will kind of filter plus k or minus k. And there's something else that I didn't talk about, and I think Amir will come in more details about it tomorrow. It's that there is also a filtering effect in k from the 8 of the NV center. We are mostly sensitive to what happens at k corresponding to 1 over the distance of the NV to the film. So we have this double filtering effect from the NV, and we have this Tarushinsky-Morier interaction, which is distorting the dispersion. And so we will be then mainly sensitive to either plus k or minus k. And I just told you, plus k and minus k produce field either above or below the film. So then we understand that the sign of DMI will decide if we expect rather noise above or rather noise below the film. This is what we measure in the experiment. And actually, you don't need this complicated synthetic antiferromagnetic texture for that. This is a calculation of the noise level that you expect as a function of DMI for a single ferromagnetic layer. Thing is that it's easier to do the experiment with the NV with the synthetic antiferromagnet because you have smaller fields coming from the sample. But basically, it should work exactly the same. This brings me to the end. So I've shown you how you can localize and actually even characterize magnetic textures, just looking at the thermal noise coming from spin waves that are excited in your sample at room temperature. And that you actually can just look at the PL emitted by the NV center. Nothing fancy. No, you don't even need microwave. It's very, very simple experiment. And before I finish, I, of course, need to thank all the people that participated to this work, in particular the people in Montpellier who did part of the experiments, and the people in Palaiseau and Grenoble who grew the samples, and our colleague Jovan Kim, also in Palaiseau, who did all the calculations. And there are not so many students around, but if I have positions available, so if you're interested, just contact me.